So today we want to start talking about the model of execution. The namesake of this learning objective, it's program execution. Today we're finally going to start talking about program execution for the last couple days of this learning objective. The objective kind of gets dominated by introduction to Scala. I got a lot of Scala syntax, like all of it, to expose you to. And then we put unit testing in here too. Unit testing is kind of program execution. You're understanding things about how your program runs a little bit. But now we're going to get into some program execution proper. Really respect the name of the learning objective. So first, I want to talk about interpretation and compilation for a bit. I won't spend too much time on this one, but I want you to be aware of what interpretation and compilation are. Especially if you've never heard these before. Let's talk about what they are and with a focus on how it actually affects us as developers. There's a lot of meaningful differences between these two underneath the hood, but I want to focus on how does it affect our lives. And then we'll get into memory diagrams, of course. So interpretation, this is when your code is read and executed line by line. This is where your code is executed. The interpreter starts at line 1, runs line 1, goes to line 2, runs line 2, etc. throughout the entire program. Compilation, on the other hand, is when your entire code is translated into another language, and then that other language is interpreted. So with compilation, your code isn't actually ran, it's translated, and then that translation is ran. So a big difference between these two. Most of the time, well, I shouldn't say it, but some of the time you won't care which one is happening, but sometimes you will. So Python and JavaScript, so last semester in 115, if you took 115 here, those were both interpreted languages. You ran your code, and your code was ran. You actually ran your code. The interpreter read line 1, read line 2, etc. throughout the entire program, and ran your code that way. One feature of this, of why it matters to us, when we're writing code, is that we're going to see more runtime errors. In 115, you probably saw a lot of runtime errors where you run your program runs, and then during the time that it's running, during runtime, your program crashes. You get to a point where your program just doesn't know what to do, and it just stops. It says, error, don't know what to do here, and just stops. So here's an example. Again, just like my early Scala examples, I'll say the same thing here. There's some syntax here that you haven't seen before, but I'm still confident that you can read this code and understand that it's going to print 15 to the screen in the end. It's going to add 5 and 10 and print 15, even if you don't know exactly how it's doing that. So we're going to create a variable and set it to the value 5. We're going to call this method. It's going to print adding to state to the screen. It's going to add 10 to the 5. And then it's going to print out 15. Yay, we printed 15 to the screen. Here's that same program, except instead of giving it the integer 10, I'm going to give it the string ten, and I'm going to add that to 5. So when you're running Python, it starts at line 1, runs all this to define our class. Actually it does that. Gets to the main method, starts actually running code. It's going to run this line, initialize this state variable to 5. It's going to call add to state, print this line to the screen, and then try to add the integer 5 with the string 10. At this point, your program crashes. You get a type mismatch error, expected int found string, and everything breaks. Everything blows up. What's important here is that this line was printed to the screen. Your code was executing line by line, so this line was executed, and then on the following line, your program crashed. This is an interpreted language because your code is being ran directly by the interpreter. Compare that with compilation. Scala, Java, C, C++ are examples of compiled languages. So Scala, this semester, you'll experience a compiled language. Instead, now you're going to have your entire code translated and then executed. So if something goes wrong with that translation process, when your code is being translated to another language, things break. And your code never gets to the point where that translated code can execute. Nothing gets executed because your compiler couldn't translate your code into another language. It couldn't compile your code. So this is where we're going to see a lot more compiler errors instead of runtime errors. For me, and I think most developers, I would much prefer a compiler error to a runtime error. With an interpreted language, you're somewhat guessing sometimes. You're going to write your code, run it, and just hope that it works and hope that it doesn't crash. And sometimes there will be errors in your code that you don't even find. I did this with a grader one time. It's really frustrating. Where there's errors that you don't find. If you have a conditional, maybe you have an if, elif, else, and you have an error in one of those code blocks, in one of the elifs, for example, and you got your code, it's all written, you run it a few times, and it doesn't crash, and then you deploy that code, and as soon as somebody hits that elif with the error, it crashes. And you had no idea that error was there because it's a runtime error. I did that with a grader. There was one elif that I didn't check, and students were complaining that the grader kept crashing, and it certainly was because I had an error in my Python. With a compiler error, your code can never run. It's going to tell you about that error immediately, and you're going to be able to fix it. You'll get the red squiggles in IntelliJ. It'll say, hey, you got a type mismatch error here. Fix this, or I'm not compiling your code, because the compiler can't figure out how to compile your code. It doesn't know how to compile it into the other language. So this is the same example as before. We're going to initialize a variable to 5. We're going to try to add 10 to it, and everything's fine. We print 15 to the screen. When we change 10 to a string, this line is going to have a compiler error. It's going to say, hey, you have a method that takes an int, but you gave me a string. That's not cool. And it's not going to compile your code. So your code never gets to run. This line never gets to print. It doesn't get to this line where the error would actually have effect because you can't even run any of your code. Nothing gets executed. Nothing's ran. You have to fix your error before running your code. I like compilers because it helps me find the errors before they become issues. The compiler, maybe you'll get annoyed with the compiler. Sometimes it's going to constantly yell at you. Found unit, expected int. You've probably seen that one already. Or found unit, expected double. You might have come across that. But what it's doing is making sure that the errors aren't there before running your code. So by the time your code actually runs, you can be reasonably confident that it's mostly error-free. You can still get runtime errors in Scala, but most of those would-be runtime errors are now compiler errors, and the compiler is going to let you know right away. As soon as you type that error, it's going to be like, hey, maybe you should fix that. And, take a second look. And you get to fix that error right away before it becomes a big issue. Scala compiles to Java bytecode is the language that it compiles into. Java bytecode is, as the name implies, is the code that Java also compiles into. Java compiles to Java bytecode. Scala also compiles to Java bytecode. So when you compile Scala code, it's as though it were originally Java code. It behaves the same way, which means it can run on what's called the JVM, the Java Virtual Machine, which if you've ever seen these dialog boxes, you've probably seen them quite a bit, where Java wants to update Java, all this crap. That's the JVM. That's the JVM saying, hey, there's a new version. I need a new version of that JVM, which means the JVM's running on your machine, which means you can run compiled Java or Scala code. And we actually do run Java and Scala code, not simultaneously, but we mix them in the same project quite often. Even the Scala standard library uses a lot of Java code. The Scala math library is just the Java math library. It says, I'm not creating a new math library. I'm just going to use the Java math library. Why would I recreate all that? Which I think, if I'm not mistaken, I believe Scala does have a redundant math library that is in Scala, but by default, the capital M math is going to be the Java math library. So we do use Java code in this class. Scala, the language itself, uses a bit of Java code. You can mix and match them in the same program because when they're compiled, they each get their respective compiler ran, and it just compiles into Java bytecode. It's all the same on the other side, and it all just runs on the JVM. We'll use some libraries in this course, specifically the The GUI libraries will see, you'll actually be importing Java code into your project. You won't really know, you won't really care. You'll know because you'll say import JavaFX. But you won't care that it came from Java code because it's going to behave just like it were Scala code, just going to work the same. I had a thought and I completely lost it. Maybe chat will help. No, no chat. Any questions on interpretation and compilation? Because that's all I want to say about it. Just 10 minutes of one lecture, that's it. So the big difference to you, so besides more compilation errors and less runtime errors, you've already noticed the other feature of this, the other side effect, is that when you ran your Python or JavaScript code, you click go and it goes. It's because there's nothing to do except start running your code. When you click go in IntelliJ, it's going to take a bit. It takes a bit. There's a progress bar on the bottom. That's not just IntelliJ being slow as opposed to JavaScript and Python. It's not just IntelliJ being slow. It's not just Scala being slow. That's the compiler running. That's the compiler translating your code into Java bytecode and then running the Java bytecode. So if you click go, it takes a while, especially if you're running the examples repo. There's quite a bit of code there, and it all has to be compiled. You can't just compile what you're running. It's going to compile the entire project. All of that gets compiled, at least in IntelliJ, that's the default behavior. All of it gets compiled, and then your one program that you're trying to run is going to execute. So all of it gets compiled, which does imply if you have an error way over here in your project in this file over here, and you're trying to run this file over here, which is perfect and amazing, this error over here is going to prevent the compilation, and you won't be able to run your code. But you will see that compilation process. It takes a while. But if you run it and then run it again right after, it's going to run a lot quicker because it doesn't have to recompile. It's going to say, oh, there's no changes. I'm just going to use the compiled code that I already have and just run it again. All right. Good. Yes? Yes. So if you click the build button, it just compiles but doesn't run. If you click the run button, it'll compile if necessary. If there's changes detected, it'll compile and then run. Any other questions about this? Because I won't revisit it in a lecture. That's the basics that I want you to know about interpretation and compilation. Just because you are switching from an interpreted language to a compiled language, if you took 115 here, that I want to get that out there of why you're seeing some differences in Scala. Yeah. If commenting out the code with an error and recompiling, yeah. Yeah, as long as you don't need that code for what you're running. So in my example, you got an error over here, you're running over here. Sometimes if this file isn't a dependency, if I don't import that in any other files, I might just comment the whole thing. Control-A, Control/, comment out the whole frickin' file, and then run whatever I'm working on. And then I'll get back to that other thing later. It depends on how you got in that situation. It's going to be case by case. However you got in that situation, like if that error has to be fixed, like you might as well go and fix it also. But if you're really not concerned about that, also why did you change code and just leave an error and walk away from it? It just depends how you got in that situation. If it's a work in progress and you just don't want to think about it anymore at the moment, just comment it out. If it's something that needs to get fixed at that time, fix it. It just depends on the situation. Like if you go to this example in the repo, I'll have a lot of this, not a lot of this, I'll have this line commented out, or else the entire project would always be broken. You wouldn't be able to run any examples without fixing it. All right. Anything else on interpretation, compilation before we leave this behind in the dust? Memory diagrams. Memory diagrams we will not leave behind in the dust. We'll be talking about this all semester, so get used to memory diagrams. Today I want to give you some background on memory diagrams and then show you the basic structure of a memory diagram. If you had lab yesterday, lab got ahead of lecture a little bit, just the way the schedule worked out. So hopefully the TAs did a great job of explaining what memory diagrams are, but I will be talking about them in lecture also today and Friday. Next week will be examples, and then for the rest of the semester, it'll be sprinkled into each learning objective. So let's get some background on what these things actually are and how we get to memory diagrams. So when I say memory, at least in this course, I mean RAM, random access memory, which is your RAM sticks, which you all have in your laptops and in your desktops. We all have these RAM sticks, which are effectively a giant array with indices going up to the size of your RAM. Billions of indices, billions of values that can be stored in this array, in this memory. This is going back to arrays, the data structure in Scala. I called that random access memory because you can access any value by index. Same thing here. We have random access memory. You can access any value on this stick by its index. You say, give me the value at index whatever, or what we call memory addresses, and you can access that value directly. And this is where all of our data for our programs is going to be stored. Every time you declare a variable or call a method, it's all happening in RAM, all happening in memory. Memory is much, much faster than hard drive, but also much, much more expensive. You can get, even if you have a solid-state hard drive, RAM is much faster, much more efficient, I shouldn't say efficient, but much faster than your hard disk. They're both ways of storing data, but RAM is made to be much faster. This is like our working area where our programs are actually going to do the work, and then disk is for more long-term storage. Our cities.csv file is going to sit on the disk, but once we read that, we're going to read it into memory to be able to work with it, because working on disk, very, very slow. RAM is also way more expensive. You can buy a terabyte of hard disks these days, pretty cheap, not crazy expensive at all. Try buying a terabyte of RAM. It's going to cost you, and even if you do buy it, you're not going to be able to fit it in your computer. It's just, you're not going to have enough slots for it. Much more expensive, but much faster. If it wasn't so expensive, we would just use RAM instead of our hard disk, which would be pretty fun. It'd be nice to have terabytes of RAM and just use that as hard disk, but anyway. When we start our program, we need a section of that RAM. So our operating system is going to control RAM, is going to control memory, and control who can access. When I say who, I mean which processes. Which process can access which parts of memory. More specifically, in our case, the JVM is going to talk to the OS, and we're going to talk to the JVM. But I'll usually just say OS, because in general, that's how it's going to work. Our programs have to somehow get memory from the operating system and get that memory allocated for our program. So our program starts, we say, hey, operating system, give me a chunk of memory. And it's going to slice up a piece of that RAM and give us this space to work with for our program, and that's where our stuff is going to go. This is what we're going to call the memory stack. Right on the other side, each side of this stick, we don't have access to that memory. We can't use that space. It might be used by another program. It might be unused, but we just don't have permission from the operating system to access it. So we have to stay in the confines of our slice of memory that we were given, which is way bigger than we'll ever need, by the way. We'll have plenty of memory to work with, unless we're doing really silly things, or as we'll see next week, if we have infinite recursion. These are the only times we're going to have to worry about the size of the stack. So the memory stack, this is where all our values are going to be stored that our program needs. This is going to be a last in, first out data structure. We'll talk about stacks more in depth when we get quite a bit later in the semester. But what we need to know right now, the TLDR of it, think of a stack of papers. I put a stack of paper down and I pile up papers on top of that. I can only access the piece of paper on top, and I can only remove the piece of paper from top. I can't go to the middle of the stack and remove some. Physically, I could with a stack of papers, but a stack data structure isn't going to allow that. It's only the top of the stack, or as we'll see in a few slides, the top stack frame is the only active part of the stack and the only part of the stack that we can access. So the stack is where all our variables are going to be stored. And whenever we call a method, it's also going to keep track of our method calls. I said a few slides. I guess it's the very next slide. Whenever we call a method, we're going to create what's called a stack frame on the stack. This is a very important concept for stack memory. A stack frame is going to be an isolated section of the stack. And whatever stack frame, whatever method is currently running, its stack frame is the only part of the stack that can be read, and it's the only part of the stack that can be removed from the stack. Once a method ends, that stack frame is removed from the stack, and execution goes back to the previous stack frame, whatever one was underneath that one on the stack. It's very important to have these isolated environments. So for example, we could have this problem where we have the same variable name being used multiple times. Now we can do this. We've seen this before. I think a few of my examples already I've done this. If we didn't have a concept of stack frames and we're just putting everything, storing all of our variables on the stack, say I create a variable x, put it on the stack, and then I say, hey stack, give me the value for the variable x. It's just going to give me whatever I stored in x. That's all fine. Now what if I have a variable x, and then I use the math library. I want to compute, say, the absolute value of x. And that absolute value method in the math library has a parameter named x. Now when it asks the stack, hey, give me the value for x, what value does it give it if it's reusing variable names? I guess in that example they would both have the same value, but if they have different values, if I want the absolute value of x plus 1, if they have different values, which x is accessed? The solution is stack frames. The x from inside the method is the only x that's accessible, and that is in complete isolation. You can only access variables from the current stack frame, the method that's currently running, and you can't access the other x. You can't hop across stack frames at all. If this weren't the case, every single time you write a method, or every single time somebody writing a library writes a method that we're all going to call, like the math library, they'd have to say, okay, if you call this method, here's the list of variable names you can no longer use. We don't want that. That'd be crazy. Stack frames saves us from this. It runs each method in isolation, and once that method ends, that stack frame is removed from the stack. It completely disappears from memory, and there's no trace of its existence after the method returns. Yep, stack frames are part of the memory stack. At the end of lecture, I'll have an example. I'm going to do our first memory diagram, but I want to get all the concepts out there in bullet points, and then I'll visualize it in a memory diagram. So if it doesn't make sense from the bullet points, I'm going to reinforce it with a diagram, because I know there's a lot of abstract things that I'm saying here. In our memory diagram, stack frames are going to be denoted by solid boxes. Please note that a stack frame is not a solid box. This is a little bit of a nuanced point, but we always get this in interviews, which I can't believe our first quiz and interview is next week already. The semester's starting to fly by a little bit. You're going to get an interview question. I can just about guarantee it. It'll probably be worded just like this. What is a stack frame? It's probably going to be an interview question. And then based on your answer, the TAs will ask you various follow-ups to really make sure you understand what a stack frame is. And one of the answers we get all the time is, a stack frame is a solid box in our memory diagrams. It's not really wrong, but it's not showing that you understand what a stack frame is, what it really means to have a stack frame on the stack. It is represented by a solid box in our memory diagrams. But when the TA asks that question, they're looking for you to understand what a stack frame really is, not just how we represent it in our memory diagrams. So I just want to get that out there because my TA said a lot of the answers in that interview were just, oh, it's the solid boxes. But it doesn't really show an understanding of what a stack frame is, just how we draw it. I want to know this kind of stuff when they ask about a stack frame. Code blocks and variable scope. I'll have a big example on Friday to talk about code blocks and variable scope in more depth, but I want to get the concept out there, so the next 4 lectures are just examples. I'm going to reinforce, which means I get 2 lectures before anybody's lab quiz to give you a bunch of examples. So code blocks is going to be whenever we have braces in our code, at least in Scala. These are our conditionals our if, our else if, our else's, our while loops, our for loops. Which I haven't shown you a while loop, but it's the same syntax as, oh yeah, that's the problem. We don't do while loops in 115. Oh, I dug myself a hole. A while loop is like an if statement that keeps looping until the conditional is false. That's my one-liner for what a while loop is. Anytime you have the curly braces, that's a code block. With the exception of method curly braces, that is a code block, but in memory we treat it a little different because it creates a new stack frame. But with the exception of the method code blocks, every other code block is going to create a code block in our memory diagram, which is going to be similar to a stack frame, but a little bit different. So the big difference is that we can jump across code blocks. We can access variables that are declared outside of the current code block. And it's very important that we can. We do this all the time. We've done this in examples already in lecture. You've done it through 115. We can access variables outside of the current code block, but we can't have variables with the same name inside the same code block unless that code block itself contains another code block, and we can declare a variable with the same name inside that. Once we reach the open brace, a code block is created. Any variables that we declare inside the code block will go inside the code block visually in our memory diagram. And when we hit the closing brace, that code block is removed from the stack, and any variables that were declared inside the code block are destroyed. They're removed from the stack, they no longer exist, and they can't be accessed. So this is one of the things you've seen almost certainly in 115 that you've done on one of your homeworks that will drive you nuts. Let me explain the example. You have some method. Inside that method, you have a conditional, or let's use a loop. You have a loop, and inside that loop, you declare a variable. You say variable result equals whatever, and you compute what you need to compute. And then after that loop, you say return result. And what do you get? Variable not found. And you go absolutely insane. You look at your code, you say, I declared it right frickin' there. It's right there. How can you not find it? I can find it easy. It's right there. Yeah, you might bang your head against it until you figure it out. You might go to office hours and have the TAs help you out. And what the answer will be is declare that variable before your loop, do whatever you need to process inside the loop, and then after the loop, return that variable. And then it works, and you're like, wow, why the hell does that work and it didn't before? It's because when you hit the end of a code block, any variables declared inside that code block are destroyed. So that variable existed at one point in time, but when you hit the end of your loop, it ceased to exist, and then you tried to return it, and there was nothing to return because that variable was removed from the stack. So now in 116, we want to understand why that all is the case, so we'll make sure you all see and can explain why that is the case. In 115, we kind of just say, declare your variable before the block, and it's fine. Maybe you'll get a more in-depth explanation, but you're not held to it too much. You just have to memorize that. But we can access variables outside of the loop, so when you do declare it before the loop, you can jump code blocks. You're inside one code block, but you can access that variable that was declared before that code block. So we can access variables outside the current code block, unlike stack frames. We denote code blocks using dashed boxes, which kind of denotes that they're semi-permeable. We can access variables outside of the code block. Again, I'll have a much more in-depth code block and variable scope example on Friday. Today, I want just a basic example, which is going to show the structure of a stack frame and structure of a memory diagram. I'll get there, and putting one stack frame on that memory diagram. When we draw these memory diagrams, they're going to be split into the stack and the heap. We haven't talked about heap yet. It's not gonna be a big deal quite yet, but I want to get you used to seeing the heap drawn on the memory diagram because it will come into play much more later on in the semester. And very briefly this semester, we will put arrays on the heap. Your quiz will have one of those. I'll show you how to do that. I have to do that Friday, don't I? On Friday. So what's stored where? All these values are going to be stored on the stack. Double, float, int, long, short. Short is a 16-bit integer value. Char, which is a single character as opposed to a string, which is multiple characters. One character. Byte, which is an 8-bit integer value. Unsigned, for what it's worth. Booleans and strings with an asterisk. These values are all stored on the stack directly. So stack, we're going to store variables on the stack, and their values, if they're any one of these types, are stored directly on the stack in stack memory. With the exception of string, I have two disclaimers. And everything else is on the heap. I have two disclaimers here. String is actually a bit more complex than that. They're not stored on the string in actuality, in reality. They're stored on the heap. But the way they behave, strings are what we call an immutable type. They cannot change. And the way they behave because of that means that they behave exactly like they were on the stack. So for this class, we're just going to throw them on the stack and call it a day. I'm going to let the 220 instructor straighten that out. They'll say, no, Jesse's full of crap. Those things go on the heap. This is how they work. But by then, you'll be so used to memory diagrams that it'll be easy to just slide them over onto the heap. So in this class, in your memory diagrams, we're going to put strings on on the stack to avoid the extra complexity of that, because they do behave as though they're on the stack. So we're just going to simplify those a little bit. It is technically incorrect, but that's the way we're going to draw our memory diagrams here. And my other disclaimer, certain versions of certain compilers, certain versions of JVMs, they may or may not, for all I know, might not even need this disclaimer, but they do have the option to put things in different places. Something that's supposed to go on the heap, they might throw on the stack. Something that's supposed to go on the stack, they might throw on the heap. We're going to, in our memory diagrams, go off of not what's highlighted, but go off of this. And that's going to determine what goes on the stack and what goes on the heap. Because that's how everything's going to behave when our programs execute. Even if the JVM and a compiler put things in different spots, they're still going to behave the same way. So we're going to draw our memory diagrams that way, the way they behave, so we can learn computer science, learn the underlying concept, and not get caught up on, well, technically this version of the JVM actually puts this value over here and whatnot. We're not going to play those games and do that. I want you to know the concept of memory, stack, and heap, and not get bogged down with the details. That's also why strings going on the stack. I want you to just understand this concept and not get bogged down with, well, in Scala, it's like this, so let's put it over here. Nah, I don't want to do any of that. I want you to understand how memory works. And then if you're really interested in compilers and interpreters down the road and the JVM and all that, feel free to dive into that to your heart's content. In 116, it's not. Let's just not. So these values go on the stack directly. Double, float, int, long, short, char, byte, boolean, string. We're going to draw those on the stack directly. Everything else goes on the heap. Everything else. There's only three things that we know of that's part of everything else right now: array, list, and map. Those will go on the heap. But if it's not one of these, this is a comprehensive list. If it's not one of these, which is why I added short and byte, which we haven't talked about before, this is a comprehensive list. This is everything in Scala that goes on the heap. I call these primitive values, with the exception of string is never a primitive. Scala doesn't have primitives, which is why I put in quotes, but they do get compiled down to primitives in Java bytecode. So they behave as though they were Java primitives. But for what it's worth, those of you who know some Java, Scala doesn't have any primitives. I can't put lowercase letters on these and have things work. There are no primitives. But they behave like primitives. Okay, disclaimers out of the way. So down the road when you say, oh, wait, things didn't actually work like that, don't come back to me and be like, hey, you taught me the wrong thing. I'm just going to point to this disclaimer and say, yeah, but I did what I had to do for 116. or else you're going to have to draw. Strings get messy. The memory diagrams get real messy if you do it accurately. I don't want to put you through that. So let's do our first memory diagram. We're going to go through this program. This is slightly modified from code that I showed you, the second example I've ever showed you in this course. The only difference is I changed these vars to vals, and I stored the output in a variable before returning it. So we have one extra variable going in our stack diagram, just so I can show you more stuff. So let's go through our very first memory diagram. Before I go into it in too much depth, I want to show or remind you, we do have this memory diagram reference, one of the links at the top of the course website. This is made by Paul, who co-teaches 116 in the spring semesters. This is everything you need to know for the entire semester about memory diagrams. It'll go through everything we're going to talk about. This is your reference if you have a question about memory diagrams, if you want to get ahead of lecture, you're eager to see how the heap and references work. This is your reference that you can use to see how things behave. I'll be perfectly honest, when I forget some of the more nuanced points with memory diagrams, I refer to this. Like, this is our source of truth. Paul and I talked at length about all the little minor nuanced points of where should this thing go on how should we represent this on the stack. All those answers went into this document, so this is our source of truth of how memory diagrams work. You get points off on you fail a lab quiz, but you did it according to this document. Show me, I'll give you your points. I'll give you your credit for that. This is the truth for memory diagrams. All right. So to start a memory diagram, we start our structure like this, and there will be a lot of just notation, syntax, structure, things that I'll show you that for better or worse, you just have to memorize and know what the structure is of how to draw these memory diagrams. One of them is splitting it into these columns, stack, heap, and stack is split into name and value. Name is going to be the name of our variables. Value is going to be the value stored in those variables. So we start by setting up stack and heap. We won't use any heap space for this diagram, for this program, but I just wanted to get used to seeing the heap there for when it does become important. And then stack. And then we're going to create a separate section. Wherever you find room to put this, I know I'm not using the heap, so I'm going to borrow some space from the heap. In/out, or IO, or input/output, whatever you want to call it. I'll always call it in/out, short for input/output. This is where everything that's printed to the screen is going to go. You're going to draw everything that got printed to the screen right here. So we're going to start execution with our main method and start filling in our memory diagram. So the very first thing, we're declaring a variable, naming it x, and assigning it the value 7.0. So all our variables go on our stack. We're going to put the value x, a variable named x on the stack with the value 7. Fairly straightforward, I hope you agree, but I want to get all of the notation, all the structure out there. Stack memory, and this is actually what's happening on the stack in our physical memory sticks, our RAM sticks, and this is how we're going to visualize it in our memory diagrams. Name and value under the stack, then heap, which we're not doing anything with, and then input/output. So the name x stores the value 7. Next, we have a method call. So I'm introducing a bit more syntax here. We have the solid block, the solid box, to denote a new stack frame being created when this method is called. Every method call creates a new stack frame, which is an isolated environment for that method call. On the side, I'm going to write the name of the method that's being called to denote that this is a stack frame created for the multiply by 2 method. I'm going to declare the variable where the return value is going to go, but I'm not going to give it a value yet. And then I'm going to draw an arrow. The final piece of this, I'm going to draw one arrow, which is going to denote where the return value is going to go when this method executes. So the arrow goes from your stack frame to wherever the return value is going to end up. Paul and I had a debate of when to draw this arrow, and the TAs took Paul's side for what it's worth. So they draw the arrow after the method returns. I like to draw it before. I don't care what you do, as long as when you hand in your quiz, that arrow exists and it's there. I don't care when you drew it. I won't even know. When we grade your quizzes, we won't even know when you drew it. I don't care. I like to draw it first, personally, because then by the time this method is done and I'm ready to return the value, I don't have to think about where it's returning to. I'm just going to follow the arrow that I drew earlier when I was thinking about it. So I like to draw it first. When the method call happens, the very first thing we need to do is create inside the stack frame all of the parameters. So I'm going to create variables for each parameter, just one in this case, input. I'm going to create a variable for that inside the stack frame and assign it to the value of the argument. So the argument was x. This is the first of many times I'll go through this one. I'll do it twice in this example even. X, I could look up here and be like, oh, x is 7. Sure. But the advantage of a memory diagram, when you're tracing through your code and drawing a memory diagram, is I'm going to look at the memory diagram itself. I'm in the main stack frame, which we don't draw a box for the main stack frame, which implied that everything's inside a main stack frame. I look inside the main stack frame, I look for a variable named x, and I look up its value 7. So this x resolves to 7 because that's what's stored on the stack. So I create my variable for my parameter and assign it the value of the argument. Now with 7, the memory diagram didn't help us much. But if we had var x and we did a whole bunch of math and changed x 17 different times, and we traced all those changes in our memory diagram, I'm not going to redo all that work and all that math. I'm just going to look at my memory diagram and see what the value of x is. That's where it's really going to be handy, looking here instead of here. For this case, it doesn't really save us anything. We're declaring a new value output. And now we want to do the same thing again. Okay, we have to look up what input is so we can multiply it by 2. Now I can look at the code and be like, okay, input was the parameter which was called over here. I'm at this call, which it got x, and it looks like x was 7. I can trace through my code and figure out what that value is, or I can do none of that and say input, and do this is what the JVM, Scala, this is what is actually going to happen. It's going to look up input on the stack frame. Input is 7, so it's 7. I just saved a few steps. I don't really have to think too hard about what input is. It's 7 because it's right there in memory. Multiply 7 by 2, and of course I'm going to get 14 as the value of output. And then I reach my return value. I'm at the last expression of this method call. I look up, okay, the expression is just output. Output resolves to its value of 14. So I'm going to return 14. When we return and end a stack frame, we're going to put the return value. This is where I don't want to remember, okay, where was this going? I'm just going to follow the arrow and not think about it too hard. Okay, it goes into result. Again, for this example, you know where it's going to go. But when the examples get more complicated, I'm just going to follow the arrow. 14, and then we're going to cross out the stack frame. In memory, what's actually happening is input and output and that whole stack frame are being removed from the stack. They're being popped off the top of the stack, and whatever stack frame was underneath it, in this case, the main stack frame, that's what's going to resume execution. So to denote that those values and that stack frame are no longer in memory, we're going to cross it out. So on your memory diagrams in your quiz, cross that thing out. Whenever a method ends, cross out the stack frame. And execution resumes in the main stack frame. And we print 14.0 to the screen. The value of result, 14.0, print to the screen. Yeah, the return arrow, I would forget also if I didn't. I would draw it right away as well. There's another reason too. So you don't forget to draw your arrow. If you're drawing your arrow when the value is being returned, you might just put 14 next to result and forget to draw your arrow. I would draw it right when you're doing your box and doing your bookkeeping, writing this, get the arrow in there right away. Don't forget about it. And when we're grading the quizzes, like there's the two boundaries, one for the learning objective, one for the application objective for the first round for each quiz, if you recall from way back in day one when I was explaining all that, or review the syllabus. But anyway, when we're figuring out those boundaries, is this submission worthy of an application objective specifically? For the learning objective, you can make a little bit of mistakes and still get it. But for the application objective, you should be perfect to get the application objective, but there are little syntactical things that we're going to forgive. If you don't draw that arrow, but you have everything else perfect, I want to give you the credit for that application objective. If you make too many mistakes, if you don't have the arrow and you don't have this, and you didn't cross out your code block, well, at that point, I got to say, does this submission prove that you do completely understand how stack frames work, or did you just make some silly mistakes? That one's a bit tougher, but if all you forget was the arrow, you probably understand the concept that I want you to know. So I want to give you the credit there. As long as you don't have any like actual errors. If all these values are correct, if this is here and it's correct and everything, I want to give you the points for that. I want to give you the credit. And if this were a quiz question, this is what you would submit. And then we'd look at that. And the idea of all the structure of these memory diagrams is we can look at this and be assured that you understood the entire execution of this program. Like even though that crossed out box isn't in memory anymore, we're not going to have you physically erase it because then we don't know that you knew that that stack frame was there and then was removed and in which order. If there were 5 stack frames in this that are all crossed out, I want to know that they were written in the right order, not erased and then redrawn. So this is your submission. This is all we would see. And if I see this submission, I know that you got everything in the right order. You did everything, understood how this program executes, understand what's happening in memory when it executes, and you get full credit on this thing. Any questions on that? Yes? So the heap we haven't talked about yet. This is where everything else is going to go. Starting with our arrays will be the first thing we see on the heap. I might never put a map on the heap, to be honest. Linked list later in the semester, and in 2 weeks we're going to start seeing objects on the heap. But right now I just want you to know that heap will be a thing, so I'm going to draw it in my memory diagrams, even though we're not using it yet, till Friday. Yeah? So in this class at least, we won't have any input. This will just be output. I don't know why we put in, out, actually. I don't know what we would write for an input. Technically, this args would be on the stack, but we don't use it in this class, so we're not going to put it on. It would just be one extra thing you have to put on every memory diagram. I'm not going to make you do that. But args would be the input to the main method, and it would go on the stack with a reference to an array that's on the heap. All right, anything else? I was bad last semester about starting lecture questions like at 50 on the hour. This one, I think we only need a minute to do, so I'm comfortable doing this one at 49. But usually I'll try to give you 5 minutes to do the lecture question. And I'll see you all Friday.